Okay, I'm going to show you how to run heat in the graphical user interface mode, the GUI mode, from the appImage in this video. So the first thing I'm going to do is I'm going to navigate to wherever I installed the appImage. So in this case, I have it saved here. And I'm going to run it. We already made it an executable after we downloaded. And I'm not going to put any tags on it. There are a bunch of switches you can put on, like you can put on -m, but we're just going to run it like this, and it will run it in the default version, which is the GUI version. And so it starts up, sets up the environment. There's a lot of stuff printed out that you don't need to know too much about. You can see the different options for running the appImage right there. So now that it's running, the server is running, we're going to open a web browser, and we're going to browse to the address, which the default is 127.0.0.1:8050. If you don't want that default, then you can go ahead and change it with this A and P switch when you run the appImage command. But anyways, we have this graphical user interface here in our web browser. So this is heat, and we're going to go through this page and sort of fill out what we need to do an optical approximation heat flux. So I have this folder v2.0.0, which I downloaded. So this is the test case extracted. So there's a video on that, and once I've downloaded it from the GitHub releases page and extracted it, I can go in here. There's a couple different folders. There's a folder for each machine in this directory, and a batch file if we were running in terminal mode, which we're not. So we're going to go into NSTX for this machine, and we are going to see all these files here. So we're going to go through loading these into the GUI, and I'm sort of going to describe what each file does. So if we go back to the GUI here and we click NSTXU, we can load the defaults, and we see that it populates a bunch of stuff on this page. An alternative to that was we could just drop this input under -optical.csv in, and it would also populate them. If I look at that file, it's this NSTXU input optical.csv. You can see all the things that are in the GUI are basically in this file. So it's sort of a proxy for the GUI, all the inputs. And you can go through and edit these before you drop it in, and it will change the different values that get populated. And then when you're running in terminal mode, there is no GUI, so it just reads this file, and that's it. So we'll go through each of these things. So here's the shot number, 204.118, and we have a minimum and a maximum time step. You need to make sure that your G file, so the G files in this case, for the test case that you've downloaded, are 204.118, that's the shot number for NSTXU, and then this is milliseconds after the period, and so these are time steps. So this is 0 and this is 200. I've just copied 200 to 0 so that I have two of them. But you can pull them from MBS Plus or whatever you want, and then once you get them, if you name them in this G file convention, it makes it a little easier, but they don't have to be in this convention. So I'm going to load this 204.118.200 into the GUI. So I just drag and drop it in there, and then I load it, and it's loaded this. So here's the MHD equilibrium. We can zoom in. It's an interactive plot. You can do all sorts of stuff. Double click to zoom out. And you might notice this trace distance here and be wondering what that is. Well, I have a sort of an example here. If I open this up, clear that, and show you, I have two traces. So this is just an example PFC here. So it doesn't really matter. This is the PFC we're going to be talking about today in the test case, but I've picked a point on the surface and launched a field line trace. And this is a 10-degree trace right here. If I did a 360-degree trace, it would look like that. So 10 degrees is pretty short. 360 obviously goes all the way around the tokamak. So this trace distance in degrees is how far we are tracing, looking for potential other PFCs in the CAD that could be casting magnetic shadows and shielding our tile from incident heat flux. So usually a rule of thumb is to go as wide as the tile and then maybe a little bit more. So like if your tile was 10 degrees wide, go at 15 or something. But you can tune this and see what makes sense. Obviously going to higher numbers means it has to take more steps, so it will take longer. Okay, so that's the MHD box. We go into the Cad Settings box. We have the intersect resolution in millimeters. This is the resolution of all of the faces that are not in the region of interest, the ROI. So this is all the faces that are not super important in the CAD but are there, and we need to make sure that we include them for the aforementioned shadowing effects. So if you just write standard, that's a pretty good bet. You can write in a number like this if you wanted, but standard chooses a pretty optimal shape, and they're really big triangles, which is good because you want as few triangles as possible. So I usually do standard. So you can load that in, and then we need STP file. So an STP is a CAD file. So back in our test directory, we have this test case ibdh _v 2.0.0.step. I'm going to take that and just drag it in here. And it'll take a second to load, and you can look back at the terminal here and see what's happening. So it was loading it, reading it. It's NSTX, so the engineers do this weird, their coordinates are permutated, so it handles that, and then it loads it. So now we've loaded the CAD. We need to define what PFCs we want to what PFCs we're interested in. So there's two files in that folder, PFCs optical and PFCs gyro. So if we show you in that folder, there's PFCs gyro, PFCs optical. This is the optical video, so we're just going to focus on that. So I have time steps. I have this huge comment, right, that just tells you what this file is. And then I have the first row that's uncommented is time steps, PFC name, resolution, div code, intersect name, and exclude name. So time steps is the time steps we're curious about. So in the PFC name is the PFC we're interested in. So if I open the CAD for this, it's actually this is the CAD, that CAD I just showed you. So this CAD file, test case ibdh v200 step. So we're seeing here. In the CAD file, I have this PFC, solid 843. I'm going to hide this. So this PFC 843 is the one that I want to calculate the heat flux on. So that's today's challenges. Can we calculate the heat flux on this tile? And you see that I have this plane in there. I'll just mention right now, this is because I don't want to do all the calculation of every nut and bolt in this CAD and all the backing plates and the vacuum vessel and all that. So I'm just going to put a plate underneath. I know that there's bulk material and solid underneath this, but I'm just going to put this simple plane in CAD down there, and that will constrain the calculation so that there's no power flowing onto this PFC from the bottom. So if you had the real full CAD with all the backing plates and all of that stuff, it would constrain the problem. But because we don't have that, and it takes a lot longer to calculate when you have that, we're just going to put a plane in to speed up our calculations and make it go fast. So you can sort of put things into the CAD in heat and simulate different, objects in the way and stuff. But in this case, we don't really care too much about this, except for what I'm going to talk about in a second. But this is the tile we're concerned with, and you can see it's named solid 843. So we're going to go back to the let's go back to the PFC file. We can see that's the name of the PFC part, the CAD component I'm interested in. Resolution, this is millimeters, so it's 10 millimeters. So I'm going to calculate the heat flux in a 10 millimeter resolution, which is pretty coarse. We could do 5 or 1 if you want. With the flux expansion for this discharge, it'll be okay, but it's not that great. And then this is a diverter code. So I think there's a so there's a little thing about it. So it can be LO, LI, UO, UI, which is for lower inner, lower upper, lower inner, lower outer, upper inner, upper outer. And then so that's the diverter. Which diverter is this PFC in? And then the intersect name. So this is basically all of the intersects in the CAD that we care about. So if you just want to do everything, just write all. But you could write like solid 844 and then a colon, solid 842, and then a colon and all the other points you want. But just using all is fine. And then the last thing you'll notice is this Gyrosource Plane, and that's in this exclude name box, or this exclude name column. And if you remember, I turned off that in the beginning. This is for gyro orbits that I've included this plane, so it isn't really relevant for the optical approximation. And if we don't exclude it, it'll be basically shielding this PFC from the real heat flux that's going to be coming down like from top right here. So we want to exclude it in our heat flux calculation, our optical heat flux calculation, which is sort of like turning it off like what I just did. So, but we need it for the gyro orbit calculation in the CAD. So the exclude column just basically gives you an opportunity to say, I don't want to include this part. So we have the PFCs in the region of interest, and we have intersects. And the intersects are all the tiles that could be casting shadows. So like, for example, this tile, if power is flowing from right to left, could cast a shadow. And so we want all those in there, but we don't want the excess tiles, so you can exclude them if you want. So I have this file. That was probably a really long-winded description, but now you know. So you can take this PFC's optical file and just drag and drop it in here. You could also just type right into this table if you want, if you don't have a file. And you can also export this into a new CSV if you want. Or you can download a new one if you need to. So anyways, we're going to load it. And let's look at the terminal. And on my computer, I already had these meshes because I've run this test case before. But if you don't have it, it will overwrite it. And it'll overwrite it if the, even if you already have the mesh, if the step file has been modified since the last time it saw it, it will overwrite and clobber the file again. And then it shows us we have all of the potential tiles in the CAD are listed here. And for solid 843, for the line we wrote in where we did all, but we did exclude Gyrosource Plane, you can see we have all of the items in this list, but we don't have Gyrosource Plane. So that means it excluded it. So yeah, so now we've loaded the PFCs. We can come down here to the heat flux settings, and we can choose Gaussian spreading, multi-exponential, or limiter. So Gaussian spreading is like an Ike profile. Multi-exponential is like one of Dan Brunner's type profiles. And then a limiter is anything with psi n less than 1 will have a 0 heat flux. So basically, like, let's choose Gaussian spreading as the easiest one, and you can put this your own lambda q in if you want, but if you just leave it at Ike scaling and Minkowski scaling, it'll calculate it from the magnetic equilibrium for you. And if it says a scaling here, it'll ignore this box and this box. But if you put it at user defined, it'll include this box. So now that I have Ike scaling, Minkowski scaling, I'm going to define the P sol. So this is power emanating across the separatrix. So I'm just going to say 10 megawatts. And then our div codes that we said before, Li, Lo, Ui, Uo, these are defined here in terms of the power sharing fractions. So let's just say that 70% go to the outer diverter and 30% makes its way to the inner diverter. I'm going to hit no to long range intersection checking. I'm just going to load it. So now there's more stuff down here, but I don't need to do anything else. So I'm just going to come over here and I'm going to run the heat flux point cloud. And it's going to be pretty quick, hopefully. This computer has 8 cores, and heat always preserves 2 for overhead, so it's going pretty quick. So we did 10 steps, remember? So that's step 2 right there, step 3, step 4, and it's just chugging through, walking up the field lines, checking for any potential intersections with the CAD that we defined as intersects. And so then once that completes, it will write out a bunch of files. Lately I've been getting this error, so don't worry too much about it. It isn't anything serious, but this is, I think, from my graphics card. But it's going to be done in a second, and we can see that, you know, we said 10 megawatts, we said 70% goes the outer diverter, and that would be 7 megawatts. And then this tile, which is just one of several, got 6.85 megawatts. And note that this optical tessellated total power is normalized to, it's like multiplied so that it's all the way 2 pi around the machine. The true tessellated power, the sum of the power, is this. So if you take this and you do 360 degrees over the delta phi of the tile, you will get this number here. So anyways, now that I have the heat flux, I can open that. So this is ParaView, if you didn't know. So I've launched it. And there's description on how to download this on the ParaView website, and it's free. So I'm going to go to this heat directory. So your home directory / heat, and it's actually, I think it says it's still in heat here. Home, Tom, heat data, that's where you're going to go in ParaView. And you can see there I am, and I'm going to go to the data directory, and I have all of these different things because I've done a lot of different shots, but we'll just do NSTX, and remember that shot was 204.118, so we'll look in there, and it was 200 milliseconds we did. So I have a folder that has the data for that specific tile, and then this ParaView folder, which is all the tiles. So for this case, it was only one tile, so we can run this one. But I'm going to open the optical and hit apply, and you can see there's the heat flux on the surface. And it's correctly calculated that there shouldn't be anything on the bottom. There's no power on the sides. That's just on the top. Power coming down the channel, which would come down sort of along this white line here. You can see that we have a little bit of a mesh artifact going on here. So sometimes there'll be things like this, and you need to adjust your mesh resolution. Remember that resolution. The resolution for this, you can see why these dots are so far apart, is because we did 10 millimeters. This is in our PFC's optical file. So if we made that 5 millimeters, this would be many more dots on the surface. If we did 1 millimeter, it'd basically be continuous. You wouldn't even be able to see the discrete dots. So yeah, so there's the first calculation. That's how you run heat for the optical approximation. Let's say that we wanted to do a temperature simulation after that. So we have this open foam thermal analysis. First, we need to load the settings for that. So you can skip the gyro orbit box and go down to open foam. And this was 200 milliseconds, so let's just go to 0 to 250 because let's try to capture the decay after this. And this is just one point in time, so it's only going to be a single point. If you wanted to do multiple G files, you can do a time evolving discharge by just dropping multiple G files into this box. So this is just going to basically be like a delta function at 200 milliseconds with this power, and then it's going to decay off. And this is the delta T. Let's do 0.05, and these have to match 0.05. So every 50 milliseconds we'll step time forward and calculate the new temperatures, is what this is saying. And let's choose, let's do graphite. And I'm going to load those settings, and I'm going to run it. Turn off the heat flux point cloud and run the open foam thermal analysis. And you can see that it will start running. And it's going to take a minute, especially if you've never run this before for this tile. It'll take a minute because it has to create a volume mesh. I guess while this is running, I can tell you what that is. So this minimum and maximum mesh refinement levels are basically how many iterations am I going to do trying to get a volume mesh to snap to the surface mesh that heat creates. So if I do 1 to 2, that's the minimum you can do. If you want to bump it up and be a little bit better mesh, you could go to 1 to 4, 3 or 4 or 5. You could even do something like 2 to 3, or like the higher you push these numbers, the better the mesh is going to be, but it's going to take it a long time to create the mesh. And heat does save these meshes. So if you create it once, you don't have to do it again. But remember, if you change your STP file, it'll have to recreate it. So these are the controls on the refinement of your mesh. So that's up to you. So we can see it ran. Open foam run completed. It prints out some stuff that open foam had. So like each time step, the minimum and maximum temperature is sort of useful sometimes. And this is probably going to be an artifacty temperature because we're using such a blocky mesh. But you can see it was 0, 0, so it sets it initially at 300 Kelvin. And so until we get to that 200 milliseconds point where the G file is, when we said the power is turned on, and then it jumps really high, really fast. So this is probably a mesh artifact kind of thing. And then it decays off because, like I said, this was sort of a delta function. You can see this plot. So here's a table on the output tab with all of the parameters you load into the GUI, and you can save them if you want. But if we scroll down here, we can see the time history. So we have this QFVM, which is sort of a proxy for the heat flux. It's not really a good metric, but the important thing is this temperature. So you can turn that off by clicking on it, and you can see we went, and then at 2 milliseconds is when we turned on, we ramped on our function, then turned it off. And so this is sort of the up and down we get from this. And this is a pretty coarse. You should really run it higher resolution in time and space, but this is just the test case. A lot of other plots will pop up here when you running different heat functions. So yeah, so that's heat. That's how you generate the data. And if you wanted to download all that, you can just hit this button and it'll zip it into a file and download it into your downloads folder. So so yeah, that is the first video. This was how to run an optical approximation calculation from the GUI, and specifically from the appImage. Okay, this is an add-on to the video that I added after the fact, but after we ran our temperature calculation, I didn't show you how to see it in ParaView. So what we're going to do is I'm going to turn off the heat flux there. I'm going to open, and I'm going to go to the 204.118 shot number folder. And there's this open foam directory. I'm going to go into there, go into heat foam, and go into the part, and you'll see this solid843.foam file. I'm going to open that. And you can see all these different arrays that we can import. All I care really about is temperature for this example. So I'm going to hit that, hit apply. I'm going to turn off all this other stuff here. So we see, like I said, it was a 1 to 2 mesh refinement, and it's pretty crappy. It's pretty blocky. There's all these sort of artifacts going on. So I would not trust this temperature calculation too much, but it is at least a calculation. It shows you that you have the pipes hooked up. Next thing I'm going to do is I'm going to change it from a solid color to temperature, T. And this is at 2.5. The peak was at 2. And we can sort of step through time here. So just before the peak, it was at 0.15. And then if we go to right at the delta function, that's 0.2. And then it sort of decays off. So that, and this is the temperature color bar over here. We can change the color bar if you want just by using this little folder with a heart button, and you can choose from all of these different color bars. So that is how you view the temperature analysis results.